Every summer, scientists find patches of the ocean where the water has lost so much oxygen that fish and crabs suffocate or vanish, leaving only silence and a handful of strange survivors. These dead zones now number in the hundreds, expanding in places like the Gulf of Mexico, the Baltic Sea, and even Lake Erie. But are these suffocated waters just local wounds, or early warnings that the ocean itself could run out of breath? To answer that, we have to begin where it matters most, on the front lines, where collapse is already real. In the Gulf of Mexico, the arrival of summer brings a recurring transformation beneath the waves. Each year, marine scientists like Dr. Nancy Rabelais and her team at the Louisiana University's Marine Consortium set out aboard research vessels, tracing invisible boundaries where oxygen vanishes from the water. Their surveys, coordinated with NOAA, reveal a hypoxic zone that can stretch over 22,000 square kilometers, sometimes rivaling the size of New Jersey. This low oxygen patch forms off the coasts of Louisiana and Texas, mapped with precision using shipboard sensors and water samples. On deck, the data show a sharp drop in dissolved oxygen, drawing a clear line between waters where fish and shrimp can survive and a seafloor that turns eerily quiet. For local shrimpers and fishers, these maps are more than scientific records. They decide daily livelihoods. In big dead zone years, crews must steam farther from shore, burning more fuel and chasing shifting schools of shrimp and fish that crowd into the shrinking bands of oxygen-rich water. The cost of each trip rises and traditional fishing grounds become unreliable, forcing captains to adapt or risk empty nets. Dr. Rabelais recalls early skepticism from some in the industry, but decades of annual surveys have left little doubt. The dead zone returns each summer, shaped by forces far upstream. The story of the Gulf's disappearing breath is written in ship logs, catch reports, and the hard choices made by those who depend on the sea. Far to the north, the Baltic Sea holds a different kind of dead zone, one that does not simply appear and vanish with the seasons, but lingers year after year. The Baltic's geography sets the trap, a shallow, brackish basin, nearly landlocked, with only a narrow outlet to the North Sea. Fresh water from rivers pours in, but salty, oxygen-rich water from the Atlantic rarely makes it far. A permanent halocline where lighter fresh water floats above denser salt water locks deep layers away from the surface. When nutrients from agriculture, sewage, and airborne pollution sweep into the Baltic, they feed massive blooms of plankton. As these blooms die and sink, bacteria consume oxygen in the isolated bottom waters. Unlike the Gulf of Mexico, where autumn storms can briefly restore life to the seabed, the Baltic's deep basins stay cut off, and oxygen is slow to return. Long-term monitoring, coordinated by the Helsinki Commission, tracks the spread and persistence of these hypoxic zones. Scientists like Dr. Bo Gustafsson and his team have mapped the expansion. Since the 1950s, the area of low-oxygen seabed has grown more than tenfold, now covering tens of thousands of square kilometers. In some years, hydrogen sulfide seeps from the mud, making the water toxic and hostile to nearly all animal life. Fisheries that once relied on cod and flounder have watched stocks dwindle, with only a handful of hardy species able to survive the deep. The Baltic's story is a warning. When water exchange is weak and excess nutrients keep coming, a dead zone can become a chronic wound, not just a seasonal scar. In the early 1990s, the Black Sea's northwest shelf was a place few captains wanted to fish. Years of unchecked fertilizer use and wastewater had poured down the Danube, feeding dense blooms that died and sank, stripping oxygen from the water. By 1990, nearly 40,000 square kilometers, about 80% of the shelf, had become a dead zone. Nets hauled from the bottom came up heavy with jellyfish and empty of anchovies. The local fishery collapsed, and ports that once thrived on the silver flash of sprat and mackerel fell quiet. Then, almost overnight, the tide changed. The collapse of the Soviet Union in 1991 triggered a sharp decline in fertilizer and livestock across Eastern Europe. Without the constant flood of nutrients, the Danube's burden dropped by up to half within a few years. Monitoring teams from the International Commission for the Protection of the Danube River tracked the falling loads of nitrogen and phosphorus. As the pressure eased, the seasonal dead zone on the shelf began to shrink. By the mid-1990s, oxygen levels rebounded and the vast dead zone had all but disappeared. In Black Sea ports, older captains remember those years as a turning point. Jellyfish thinned, anchovies returned, and for the first time in a generation, their nets came up silver instead of slimy green. The Black Sea's recovery was not perfect. Deep waters remain anoxic, and fish stocks are still vulnerable. But the shelf's transformation stands as rare proof that a massive dead zone can retreat when the nutrient tap is turned off. This story, written in catch logs and river records, offers a glimpse of hope for other seas struggling to breathe. A dead zone begins with a surge of nutrients, nitrogen and phosphorus, carried downstream from fields, feedlots, and city drains. These nutrients pour into coastal waters, setting off a chain reaction. Phytoplankton and algae at the surface bloom in response, sometimes turning the water cloudy green or brown. When these blooms die, their remains drift downward, blanketing the deeper layers with organic matter. In the shadows below, microbes get to work, breaking down this material. As they feed, they draw oxygen from the water, steadily lowering the dissolved oxygen available to other life. Stratification locks the process in place, with warmer, lighter surface water staying on top, while cooler, denser water below is cut off from the atmosphere. Without mixing, oxygen cannot be replaced. As the microbes continue their feast, oxygen levels in the bottom water slip below 2 milligrams per litre, the threshold for hypoxia. Fish and crabs flee if they can. Those trapped on the seabed suffocate, leaving behind a zone where life thins out or disappears entirely. The journey from farm to sea is anything but straightforward. In the vast heartland drained by the Mississippi River, fields of corn and soybeans stretch horizon to horizon, supported by a steady diet of synthetic fertilizers and manure. When spring rains arrive, water races through a hidden web of tile drains beneath the soil, carrying dissolved nitrogen and phosphorus into nearby streams. These engineered shortcuts, designed to keep fields workable, deliver nutrient-rich water into rivers at a pace and scale nature never intended. Alongside the countryside, cities and towns add their own share. Treatment plants discharge wastewater that still contains significant loads of nutrients, while stormwater systems funnel runoff from lawns, streets, and parking lots directly into the watershed. The result is a powerful nutrient pipeline, pulsing each spring with the melt and rain, sending the bulk of the year's load toward the Gulf of Mexico in just a few months. Decades of this annual surge have left a legacy. Even as conservation practices improve, nutrients stored in soils and groundwater continue to seep out, creating a time lag that frustrates quick fixes. The story of dead zones is written not only in current choices, but in the accumulated memory of the land, where yesterday's decisions echo for years downstream. Not all low-oxygen waters begin with human hands. In the open ocean, there are vast natural features called oxygen minimum zones that have existed for thousands of years. These zones form hundreds of meters below the surface, shaped by slow-moving currents and the steady rain of organic material sinking from sunlit waters above. In places like the eastern tropical Pacific and the northern Indian Ocean, oxygen minimum zones stretch for thousands of kilometers, lying far from land and beyond the reach of local policies. Their boundaries shift with global circulation patterns, not with the rise and fall of fertilizer use or sewage outflows. The oxygen here is never fully replenished, and the deep layers remain breathless for centuries at a time. By contrast, coastal dead zones are shallow, close to shore, and highly reactive to what happens on land. These hypoxic patches can appear or shrink within years, responding directly to changes in runoff, wastewater, and farming practices. Unlike oxygen minimum zones, their fate is closely tied to human activity and can be managed through targeted action. Recognizing the difference matters. While natural oxygen minimum zones set the background, the expanding coastal dead zones are signals of a world where human influence now rivals the slow work of ocean currents and deep time. When dissolved oxygen drops near the seafloor, the rules of marine life change in an instant. Fish, shrimp, and crabs sense the suffocating water and move swiftly, packing into narrow bands just above the dead zone. These escape layers can turn the edges of hypoxic regions into crowded corridors, where predators and prey jostle for space and survival. Above, the water might teem with life, but just meters below, the seabed falls silent. Worms, clams, and other creatures anchored to the bottom cannot outrun the oxygen crash. As hypoxia deepens, mass die-offs leave behind patchy sediments, their surfaces littered with empty shells and the remains of animals that did not make it out in time. The chemistry of these zones grows stranger as oxygen disappears. Bacteria that thrive without oxygen take over, using nitrate or iron as substitutes. When even these run out, sulfate-reducing microbes begin to dominate, churning out hydrogen sulfide, a toxic gas that seeps from the mud and gives the water a sharp, rotten egg smell. In the Baltic's deep basins and parts of the Black Sea, hydrogen sulfide can linger for months or years, making the water milky and hostile to most animal life. The result is a landscape where only the hardiest survivors persist, and the normal rhythms of the food web are broken. These compressed habitats and chemical shifts ripple outward, reshaping entire coastal ecosystems and the fisheries that depend on them. On a humid morning in August 2014, the city of Toledo, Ohio woke to an urgent message. Do not drink, cook, or bathe with tap water. For nearly 400,000 residents, the faucets had become a source of risk instead of relief. The culprit was a massive bloom of toxic cyanobacteria, microcystis, spreading across Lake Erie's western basin. Lab tests detected microcystin, a potent liver toxin at levels exceeding World Health Organization's safety guidelines. Within hours, bottled water vanished from store shelves. The National Guard arrived with emergency supplies, and city officials fielded anxious calls from hospitals, nursing homes, and families with young children. Restaurants closed, dialysis clinics scrambled, and social media filled with images of green scum lapping at water intakes. For Lake Erie's water managers, the crisis was a stark reminder that dead zones and harmful blooms are not distant threats. They can shut down a city overnight. The bloom had been fueled by warm temperatures, calm conditions, and a surge of phosphorus from spring rains washing fertilizer and manure off farm fields upstream. When the algae died, their decay stripped oxygen from the lake's bottom waters, while the toxins they released lingered at the surface. As the crisis unfolded, water plant operators worked around the clock, adjusting treatment processes and sampling every few hours. The shutdown lasted 2 days, but the shockwaves lingered. In the aftermath, utility leaders and scientists pressed for tougher controls on nutrient runoff, warning that without change, the tap water crisis could become a recurring nightmare for cities across the Great Lakes. In several estuaries, the tide has started to turn. Along the US East Coast, decades of investment in advanced wastewater treatment have paid off. In Chesapeake Bay, treatment plants now strip far more nitrogen and phosphorus from sewage before it reaches the water. Monitoring teams from the Chesapeake Bay program track these changes each summer, recording some of the lowest hypoxic volumes in recent decades. In 2023, the bay's dead zone covered less area and lasted fewer days than the long-term average, a sign that targeted nutrient controls can yield real results, even as weather and climate still play a role. Further north, the Hudson River estuary saw oxygen levels rebound within a decade of major sewage upgrades, bringing back striped bass and blue crabs to stretches once written off as lost. These stories show that dead zones are not always permanent scars. When upstream fertilizer use drops and cities invest in cleaner water, oxygen can return, and with it, the rhythms of coastal life. The path to recovery is neither instant nor guaranteed, but the evidence is clear. Policy choices and sustained effort can help seas and estuaries catch their breath. Even after nutrient runoff drops, the ocean's memory lingers in the mud. Decades of excess fertilizer and sewage have loaded coastal sediments with a backlog of organic matter and buried nutrients. When oxygen runs low, these legacy stores begin to leak back into the water, fueling new blooms and keeping bottom waters starved of breath. Scientists call this sediment memory a hidden obstacle that can stretch recovery from years to decades. In the Baltic Sea, deep basins remain choked with hydrogen sulfide and phosphorus long after upstream pollution controls began. In Lake Erie, managers saw phosphorus levels fall at river mouths, yet the lake's central basin stayed hypoxic for years, sustained by phosphorus released from anoxic sediments each summer. Warmer temperatures and stronger stratification make matters worse, locking oxygen out of the deep and speeding up microbial recycling. As climate change intensifies, these internal feedbacks threaten to lock some seas into a cycle of recurring hypoxia, even when the external nutrient tap is turned down. The window for easy recovery narrows, not just because of what flows in today, but because of what the seabed remembers from the past. Model projections trace a troubling path for the world's coasts. The Bay of Bengal, fringed by the Ganges and Brahmaputra, is singled out for its vulnerability. Already home to natural low oxygen layers, but now facing heavier nutrient loads and warming seas that push hypoxia closer to shore. The Arabian Sea and the Persian Gulf, ringed by expanding cities and intensive agriculture, are expected to see longer and more frequent episodes of low oxygen, especially in shallow, poorly flushed bays. East Asia stands at the heart of this future risk map. Off the Yangtze and Pearl rivers, the East and South China Seas are projected to host larger, longer-lasting dead zones as fertilizer use and rapid urbanization continue. Southeast Asian estuaries from the Mekong to the Chao Phraya face similar threats as monsoon rains flush more nutrients into already stressed waters. Along Africa's Gulf of Guinea and upwelling coasts, models warn that a mix of growing agriculture and changing ocean currents could make hypoxic events more common. Sparse monitoring leaves much of this future uncertain. In the Americas, the northern Gulf of Mexico remains a chronic hotspot, with projections showing persistent or even worsening hypoxia if nutrient cuts and climate action stall. The Baltic and Black Seas, Chesapeake Bay, and select European estuaries all appear on the map as regions where climate-driven stratification could make local efforts to control nutrients less effective. Scientists agree. Unless global emissions and nutrient runoff are curbed, the map of dead zones will grow more crowded and unpredictable, redrawing the boundaries of marine life for decades to come. Right now, over 400 coastal dead zones threaten global fisheries and local economies, yet recovery in places like the Black Sea proves that action works. As climate change accelerates ocean deoxygenation, the window for easy fixes narrows. The ocean's oxygen balance remains in our hands. What we choose on land writes the future beneath the waves. Share your thoughts below and join the conversation.